Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome to the 32nd lecture of Discrete Structures CSC 102. In the previous lecture we were discussing about trees and we have discussed matrices and graph. How to construct matrices using directed graphs, undirected graphs, and how to obtain directed and indirected graphs if we are given matrices, and we have also discussed how to obtain matrices of the connected components of the graphs. And then we have started trees and some properties of trees, and we were discussing rooted trees. Today we are going to start. We shall discuss again rooted trees and then binary trees, and then we shall discuss spanning trees and shortest paths, minimal spanning trees, and Kruskal's algorithm of finding shortest paths if we are given some graph. And then we shall discuss Prim's algorithm, and at the end we shall discuss how to find a minimal spanning trees if we are given any graph, any connected graph. So what is a rooted tree? If we look at the formal definition of rooted tree, a rooted tree is a tree basically in which there is one vertex that is distinguished from the others and is called the root. The level of a vertex is the number of edges along the unique path between it and the root. We shall discuss all these points which are given in the definition of the rooted trees with the help of an example. The height of a rooted tree is the maximum level of any vertex of the tree. Given the root or any internal vertex v of a rooted tree, the children of v are all those vertices that are adjacent to v and are one level further away from the root than v. If w is a child of v, then v is called the parent of w, and two distinct vertices that are both children of same parent are called siblings. Given two distinct vertices v and w, if v lies on the unique path between w and the root, then v is an ancestor of w and w is a descendant of v. So now let's discuss all these points which are given the definition with the help of an example. Here, just to describe the terms which are in definition, here is a tree. The first point here, which is distinguished from others, this is basically called a root, where this rooted tree has been started. So this point is called a root, and this is basically a level 0 of this rooted tree. Rooted trees are basically just like the roots of a tree, therefore such type of tree are called rooted trees. Now the first point here, this is called root, where this tree started, and this is basically the level 0 of this tree. At the next level here, at the level 1, this is basically we have only these 3 branches, and these points u, for example, this one is u1, this is u2. These are basically immediate, you can say immediate next points which are connected to this rooted tree, root of this tree. So these are at basically level 1. Now let's revisit the definition. One vertex basically which is distinguished from other is called a root. We have just discussed the level of a vertex. Level of a vertex is the number of edges along the unique path between it and the root. Now here we have only one edge, and u is connected to the root, and we have only one edge here also, and at this point also we have only one edge. at this point also we have only one edge, so one edge away from the root is basically the level 1. Two edge away from the root is basically the level 2. So here we have level 2 because we have 1 2 1 2 2 edges. So similarly this one, this one, this one, all these verses are at the level 2 because there are 2 edges. So, or you can say these verses are 2 edges away from the root. So we have, therefore this level is level 2. Here we have these points are 3 edges away from the root, therefore this is level 3. These points are 4 edges, 1 2 3 4 edges away from the root, therefore this vertex is basically at level 4. So this is how we describe levels in the rooted trees. Now the height of a rooted tree. What is height of a rooted tree? Is the maximum level of any vertex of the tree. Now what is the height here in this rooted tree? It's basically 1 2 3 4. You can see the height of this tree is 5. The height of a rooted tree is the maximum level of any vertex of the tree. So here in this rooted tree we have 1 2 3 4 5. So this vertex is the maximum level of vertexes here at the end is 5. Therefore the height of this rooted tree is 5. Given the root or any internal vertex v of a rooted tree, if we are given any internal vertex is basically, it's not the, you can say, terminal vertex. These are basically terminal vertices. These are terminal vertices, as we have discussed in the previous lecture. So if we are given any internal vertex, if this vertex is not the last or the initial, you can say, so these are basically the terminal vertices, and all the vertices which are in between of them, these vertices are called internal vertices. So if we are given any internal vertex v of a rooted tree, the children of v are all those vertices that are adjacent to v and or one level further away from the root than v. Now for example, in this rooted tree, we suppose that this is v. This is an internal vertex of this rooted tree. Then one further away from, one level away from the root is basically are these vertices, this, these are all, no, this is further away, one level further away from the root than v. So only these 3 vertices are basically called the children of v, not these vertices, these one, because these are 2 level away from the root from v. So only these 3 vertices are the children of v. So now what is next is basically, if w is a child of v, then v is called parent of w. So that's why. So if we are given this, if this is basically these 3 vertices are children of v, so v is called parent of these vertices, parent of these 3 vertices. V is parent of these 3 vertices. Or you can say that if the children of, if we consider u as an internal vertex, then v and w are children of u, and v and w are children of u, and u is the parent of v and w. So this is how we describe children and parents in a rooted tree. And 2 distinct vertices that are both children of the same parent are called siblings. So similarly, if we consider here u as a parent of v and w, v and w are children of u, then v and w are called siblings here. So you can see here v is a child of u is a parent of v. Similarly, w is a child of u and u is a parent of w. V and w are called siblings. The next is if we are given any two vertices v and w, if v lies on the unique path between w and the root. If v lies on the unique path between w and the root, then v is ancestor of w and w is descendant of v. For example, here vertices in the enclosed region, this is basically dotted enclosed region here, are descendant of u. So u is basically ancestor, u is ancestor, and all these vertices which are connected with u and away from the root are basically descendant of u, and u is called ancestor of each of these vertices. So this is how we see the descendant and ancestor of the vertices in a rooted tree. So this is all. We have discussed all the main points in the definition with the help of this rooted tree. Now let's consider an example of this rooted tree. Consider the tree with root v0 or v0 shown below. Here this is basically a tree where this is the root of this rooted tree, and there are some questions which we have to answer. A part is, what is the level of v5? So v5 is here, and we have to tell the level of v5. How to determine the level of any vertex in a rooted tree is basically count the number of edges from v5 up to v0, which is the root of that rooted tree. So we have 1, 2 edges. v5 is basically 2 edges away from the v0, therefore v5 is at level 2. So all these vertices are at level 2. So this is basically level 1, as we have discussed in the definition, because these vertices are v1, v2, v3 are all 1 edge away from v0, therefore this is level 1. All these vertices are basically at level 3. Now what is the height of this rooted tree? B part is what is the level of v0? Level of v0 is basically this is at level 0, because we don't have any edge from v0 to the root, therefore its level is 0. What is the height of this rooted tree? So how many edges are there in this rooted tree? So this is basically 1, 2, 3. So the height of this rooted tree is 3. The height of this rooted tree is 3. In D part, what are the children of v3? v3. So here is v3, and one level away from the root and connected to v3 are basically v5 and v6. Therefore v5 and v6 are basically the children of v3. In E part, what is the parent of v2? v2 is here. The parent of v2 is v0, as v1, v2, v3 are the children of v0, therefore the parent of v2 is v0. In F part, what are the siblings of v8? v8 is given here. So what are the siblings of v8 are v7 and v9 are siblings of v8 according to the definition of rooted tree. The next level is what are the descendants of v3? the descendant of v3. V3 is here. All other vertices which are away from v3, means you can say further away from the rooted tree from v3, these are v5, v6 and v10. These are all descendant of v3, and v3 is basically the ancestor of all these vertices. So this is how we can describe the rooted trees and how to compute levels and parents, siblings, children, descendants, ancestors in the rooted tree. The next is which is a special case of a rooted tree, is basically binary tree. A binary tree is basically a rooted tree in which every parent has at most 2 children. So basically a binary tree is a rooted tree, and it is a special type of rooted tree in which every parent has at most means maximum you can say, या ज़्यादा से ज़्यादा 2 children हो सकते हैं, 2 children हो सकते हैं. Each child in a binary tree is designated either a left child or a right child, but not both. Means if any vertex or any parent has 2 children, then one child will be called left child and the other will be right child, but not the both, that is both the children cannot be the left child. And every parent has at most 1 left child and 1 right child. So this is the same thing. A full binary tree is a binary tree in which each parent has exactly 2 children. However, until here we have in this part of the definition, which is before this, a full binary tree. In this definition they have described that every parent can have or has at most 2 children. ज़्यादा से ज़्यादा 2 children हो सकते हैं, means अगर ज़्यादा से ज़्यादा 2 हो सकते हैं तो 1 भी हो सकता है, 0 भी हो सकता है. So a binary tree is basically a rooted tree in which each parent has at most ज़्यादा से ज़्यादा 2 children. उसमें ज़रूरी नहीं है कि exactly 2 children हो, तो 1 भी हो सकता है, 2 भी हो सकते हैं, लेकिन 2 से ज़्यादा नहीं हो सकते. But after this part of the definition, a full binary tree is a tree in which each parent has exactly 2 children. Exactly 2 children means 1 नहीं हो सकता, उसमें सिर्फ और सिर्फ हर parent के 2 children होंगे. Now, given any parent from here, given any parent v in a binary tree T, if v has a left child, then the left subtree of v is the binary tree whose root is the left child of v. Definitely you can see this figure and you'll understand better. Given any parent v in a binary tree T is any binary tree, if v is the left child, then the left subtree of v is the binary tree whose root is the left child v of v, whose vertices consist of left child of v and all its descendants, and whose edges consist of all those edges of t that connect the vertices of the left subtree. The right subtree of v is defined analogously, similarly. So for example, if we have this a binary tree whose root is this, and if we suppose it's a parent, it has 2 children, this u and w. Yes, u is the left child of this root and w is the right child of this, and further u has 2 children, this and this is v and this is, for example, this is v1 and this is v2. Then v is the left child of u and this vertex, whatever its name is, this is right child of this, and w further have 2 children, one is left, one is right, and further this has one child, and x has 2 children. this has one child, and further this has two children. So this is basically a binary tree, not a full binary tree. And you can see that this is basically the left subtree of this W, whose root is this vertex, and this is a right subtree of W, whose root is basically X. You can say, now you can read this definition and you will understand it better. Now let's consider an application of these binary trees, a representation of algebraic expressions. In computer we can introduce these algebraic expressions like this by using these binary trees. For example, if we want to express A divided by B, this is basically A divided by B, A by B. Now how to represent this algebraic expression by using this binary tree? So we write here the division. Here this symbol denotes divides, and here we have two children of this division A, B, and we read it from left to right, from here to here. For example, A divides B. This is how we read this binary tree. Now another example, if we have A divided by C plus D, this is written as basically A divided by C plus D. So now basically we have this algebraic expression, and how to express this with the help of binary tree. In the root we shall define the division, and on the left we shall write A, and on the right first we have to add C and D. So here we write plus, and there are two children of this plus, C and D. So how to write this? Basically the priority in these algebraic expressions, first we divide, then we multiply, then we add, then we subtract. Basically priority is on these operations. First we divide, binary operations, and then we multiply, then we add, and then we subtract. This is the order of preference in the algebraic expression of these binary operations. So therefore here we write the division, here we write plus. First we A divides, then C plus D. So this is again, this expression will give us the same algebraic expression. Now we consider some more general algebraic expression and how to express it with the help of binary trees. Here we have bracket, in bracket we have A minus B into C, and then we have bracket plus bracket D divides E. Even if we don't have these brackets, we can write the binary tree with the help of these order of preference. But still in the algebraic expression, as you have already know, that we give the preference to brackets. First of all, the preference is to the bracket, and then division, multiplication, and accordingly we can sort out how to simplify such type of expressions. So here we have bracket, here we have bracket. So this plus is basically joining these two brackets, so we write here plus and then two brackets. In the first bracket we have here multiplication. This dot represents multiplication. We have two numbers which are multiplying, so we write here dot, and there dot, in dot we have A minus B dot C, means here there are two children here of dot, which is one is C and the other is, basically we have to subtract A and B, so we write here minus, and then there are two children of this minus, A and B. So here how to write this, and on the right side we write division and D divide E. So this is basically one bracket and this is the other bracket. So we simplify this bracket, then plus this bracket. And how to simplify this bracket? Here we have A, how to read, as I have told you here, this will be simplified from left to right. A minus B dot C. So how to write this? This is basically A minus B. This is simplified here. This is again the bracket, and then dot. We have dot C. So one, here we have C. One bracket now is simplified. Now we have plus. Then AD divides E. So we have D divides E. So this is the other bracket. We again obtain the same algebraic expression with the help of a binary tree also. So this is how we can express binary. This is basically one of application of binary trees. We can simplify algebraic expressions using these binary trees. So this is an example of a full binary tree also. You can see that every parent has 2 children. Now let's discuss what are the spanning trees and how to find the shortest paths in the given graphs. This is an example and motivation how, why and where we need to find shortest paths, and how the trees help us to find the shortest paths. An East Coast airline company wants to expand service to Midwest and has received permission from the Federal Aviation Authority to fly any of the routes shown in the figure. So these basically एक एयरलाइन कंपनी है, जैसे कि हमारी अब फॉर एग्जांपल PIA है या एमिरेट्स है, जो भी है, वो अपना जो सर्विस है वो एक्सपेंड करना चाहती है. मींस ऑलरेडी वो कुछ शहरों पे उनकी जो फ्लाइट्स हैं वो जाती हैं, एंड दे वांट टू एक्सपेंड देयर सर्विस टू many other cities. So here we have these cities: St. Louis, Chicago, Milwaukee, Detroit, and the other here is the Minneapolis and Nashville, and there are other cities which they want to expand their service in these cities of their airline. So this is basically the graph of the cities, and we have to find a tree so that all these cities are connected. What we do and how the trees help us to find the shortest paths. So we'll find a tree which is basically a circuit tree, which connects all these paths, and they will to these cities. So this is how, in such type of problems, we need the trees, and then these type of cars are spanning trees. The fact is that the graph of any system of routes that satisfy the company is basically wishes is a tree, because if the graph were to contain a circuit, for example, if this graph contains a circuit, then one of the routes in the circuit could be removed without disconnecting the graph, and that would give a smaller total number of routes. But any tree with 8 verses have 7 edges. This is basically अगर कोई एयरलाइन है तो वो बेसिकली अगर कोई एयरलाइन है तो वो यही चाहेगी कि उसकी एयरलाइन की डेफिनेटली डिस्टेंस कम होगा तो टाइम की बचत होगी, और पेट्रोल की बचत होगी डेफिनेटली. उससे आपकी जो पैसों की बचत होगी. तो ये क्या वो कंपनी क्या चाहेगी? वो यही चाहेगी कि इस तरह कोई रूट डिफाइन किए जाएं कि सारे सिटीज़ भी कनेक्ट हो जाएं, उनकी फ़्लाइट्स वहाँ पे जाएं, और जो डिस्टेंस है वो भी मिनिमम रहे. तो सच टाइप ऑफ network basically is a tree, because for example if we have 3, 4, 5, 6, 7, 8, we have 8 cities, and we have discussed in the basic definitions of tree that if we have n verses, then a connected graph with n verses have n minus 1 edges. If this is true, then it is called basically tree. So here if we have 8 cities, then the all routes basically which connects all these, then the routes which connects all these cities is basically a tree which has 7 edges or 7 routes. So any system of routes that connects all 8 verses yet minimizes the total number of routes consists of 7 routes, basically it's a tree. So the solution to this problem, to expand the service of this airline, is basically a tree. We have to find a tree which connects all these cities and minimizes the total distance and their cost of fueling, so that they can expand their service to these cities. Now, what is the proper definition of a spanning tree? A spanning tree for a graph G is a subgraph of G that contains every vertex of G and is a tree. So spanning tree is basically a tree which is a subgraph of that given graph, and it's a tree that contains every vertex of G. So such type of tree is basically called a spanning tree. So an important result related to these spanning trees is basically which is given here in the theorem. You can see the proof of the theorem in the book of Susanna of Discrete Mathematics. The first part of this theorem is every connected graph has a spanning tree. Means if the graph is connected, then there must be a spanning tree. And second result is any two spanning trees for a graph have the same number of edges. If you have two different spanning trees which are the subgraph of G and contains every vertex of G, then both spanning trees must contain same number of edges. So this is also an important result related to these spanning trees. Now, an example in which we shall discuss how to find the spanning trees for a given graph. So example is this: find all spanning trees for the graph G pictured below. That is this is the given graph. This is the graph G, and we have to find all possible spanning trees for this graph. Now, what is spanning tree? Spanning tree is basically a tree, and tree is always a circuit free. And you can see that in graph G there is a circuit V1, V2, V4, V1, or you can say V2, V1, V4, V2. This is a circuit. So we have to remove this circuit from the graph to get a tree and then spanning tree. So any one of these three edges, this one, this one, this one, can be removed to remove this circuit from this graph, and we can get a spanning tree. If we remove the edge V2, V4, then we get this tree, and this is a tree which contains all the vertices of the graph, therefore it's a spanning tree. So this is one example of the spanning tree which we can obtain from the given graph G. And if we remove the edge V1, V2, then we obtain another spanning tree from the given graph, which is a subgraph of G and contains all the vertices of G. And at the last, if we remove V1, V4, we get this spanning tree. This is basically a tree which is circuit free and contains all the vertices of G, therefore it's a spanning tree for the given graph. So all these spanning trees are basically all these trees are spanning trees which are subgraph of G. And you can see that in a theorem every connected graph has a spanning tree. So this graph was connected, so it has a spanning tree. We can say that this result is true, and there is a proof of this result also. You can see the proof. And the second result, any two spanning trees for a graph have the same number of edges. Now you can see that all these three spanning trees have 5 edges, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5. So all these spanning trees we obtain from the same graph, therefore they must have same number of edges, and it is true in this example. You can see. Now what is the minimum spanning tree? Now consider the same example as we have discussed at the start of spanning tree, in which we have to basically an airline wants to expand their services to some other new cities, but with a route system that minimizes the total mileage. Now how to minimize the total mileage? If the company's success is to minimize the total mileage, then that will be better for that company. They will save money and fuel, as we have discussed. Now at between each two cities we have mentioned the distance between two cities. For example, from this city Minneapolis to Nashville there are 695 kilometers. The distance is basically in kilometers. So between each two cities, now we have mentioned the distance in kilometers. Now we have to find the minimum spanning tree, that is a tree which contains all the vertices of that graph and is a tree, and it's obviously a subgraph of this graph. And if this graph whose edges are labeled with numbers known as weights, and we call this, it could be weight, it could be anything, it could be distance, it could be any other thing which we can assign here in the graph, and such type of basically numbers which we label between with the edges are called weights, and we call it a minimum weight or weighted spanning tree. And we have to find a minimum weighted spanning tree, or simply a minimum spanning trees is a spanning tree for which the sum of the weights of all the edges is as small as possible. So such type of trees are called minimum spanning trees, in which all the edges are assigned weights, and weights could be anything. It could be kilometer, it could be weight, and some other things. Now what is the proper definition of a weighted graph? A weighted graph is a graph for which each edge has an associated positive real number as a weight. The sum of weights of all the edges is the total weight of the graph. A minimum spanning tree for a connected weighted graph is a spanning tree that has the least possible total weight compared to all other spanning trees for that graph. If G is the weighted graph and E is an edge of E, then W of E denotes the weight of E, and W of G denotes the total weight of that graph. Now how to find the minimum spanning trees? There are two algorithms which we shall discuss here in this lecture, but there are some other algorithms, but here we shall discuss Kruskal algorithm first and then Prim's algorithm. What is basically the Kruskal algorithm to finding minimum spanning trees? In Kruskal algorithm, the edges of a connected weighted graph are examined one by one, and Kruskal basically it's Joseph Kruskal in order of increasing weight. So we shall connect edges one by one in the order of increasing weight. At each state, the edge being examined is added to what will become the minimum spanning tree, provided that this addition doesn't create a circuit. That is, we have to care about that we don't have any circuit in that minimum spanning tree. After n-1 edges, if a graph has n vertices, these edges together with the vertices of the graph form a minimum spanning tree for that graph. That is, if we have n vertices, we have to connect n-1 edges and we will get minimum spanning trees. This algorithm is explained here on this slide. What is the input of this algorithm is basically G. G a connected weighted graph with n vertices and where n is a positive integer. And we have to build a subgraph T, which will be our minimum spanning tree of G, which consists of all the vertices of G with edges added in order of increasing weight. At each stage, let m be the number of edges of T. So how to initialize this algorithm? Initialize T to have all the vertices of G and no edges. That is, we draw all the vertices of that graph with no edges. We don't draw any edge between any two vertices. In the second step, let E be the set of all edges of G and let m is 0. That is, there is no edge in the graph. Now, while m is less than n minus 1, find an edge E in E of least weight. So first of all, we shall find edge of least weight in that graph. Now delete E from E, delete small e from E. 3C is, if addition of E to the edge set of T doesn't produce a circuit, then add E to the edge set of T and set m is equal to m plus 1, and while we'll get the T. Now let's apply this algorithm on the same graph which is given here, which is basically the same graph which we have used in which airline company wants to expand their service to some other new cities. Now, first iteration. What is the first iteration? Find the minimal find the edge which has minimum weight. So by looking at the graph, you find the edge which has minimum weight is 83, 74. This 74 is the edge basically which has minimum weight. So first of all, what you do, you basically draw these points, all these points only. So there are 1, 2, 3, 4, 5, 6, 7, 8. So 8, we have 8 vertices. This was the first step in the algorithm. Now find the edge which has minimum weight and connect the vertices. We have 74 is the minimum weight. We draw this edge. So what we have done in the first iteration. In the second iteration, find the weight which is greater than 74. Now greater than 74 is the bit basically the 83. So add here this weight, this edge between these two vertices. Similarly, find the next edge which has greater weight than 83. So which is here, you can see 151 is basically the edge which is greater than 83. So we add this edge to this graph. Next, find the edge which has greater weight than 151 is basically here, you can see 230. I think 230 is, you can see here this. At fourth step, we have weight 230 which is greater than 151. So 230 is this. So add this edge in the graph. Similarly, next weight which is greater than 230 is 242, I think. So add this edge to this graph, and the edge which is greater than 242 is 262, I think. 262, yes. So add this edge to this graph, and then find the edge which has weight greater than 262 is what is 306. It's 30. So 269, sorry, is 269, this one. But if we add this edge here, this will produce or we will have a circuit in the graph. We'll have circuit which start from here and ends at here. So this edge will give us a circuit in this tree, in this graph. Therefore we cannot add this edge to this graph. So we go further. The weight which is greater than 269 is 306. If we add up 306 here, this will give us again a circuit in this graph. So we cannot add this edge to this graph, and the weight which is greater than 306 is 348. If we add 348 here, it will give us again a circuit. So we cannot add this weight also, and we go further. A weight which is greater than 348 is 355, I think. So this is 355, and this will not give us a circuit. Therefore we add this edge. Now we have 1 2 3 4 5 6 7. We had 8 vertices and 7 edges. So we get a tree, and this tree contains every vertex of this graph. Therefore this is basically a minimum spanning tree, and this is basically the Kruskal's algorithm, and Kruskal's algorithm give us this minimal spanning tree, which is the solution for that airline company which want to expand their service to other cities. And this is, if we sum up all the weights, the total weight is basically the sum of 355 plus 74 plus 262 plus 242 plus 155 plus 83 plus 230. So this is basically the total distance in which they have to bear expenses to cover all distances, and they will initiate their service to these cities, and this will be the minimal spanning tree which will give the solution to this problem to that airline service. And we have found the minimal spanning tree using Kruskal's algorithm. Next is basically the Prim's algorithm. The Prim's algorithm to find minimal spanning tree works differently from Kruskal's algorithm. It builds a minimum spanning tree T, and the person was basically Alcatel-Lucent Technologies, in which the person is basically the Robert Prim, who born in 1921, who gave this algorithm. And this algorithm builds a minimum spanning tree basically by expanding outward in connected links from some vertex. In Kruskal algorithm, we just find the minimum weight among all the weights in the graph, and we start by adding that edge to the graph, to the vertices, or you can say to the graph, and we increase the weights accordingly that to obtain the minimal spanning tree. But in Prim's algorithm, we have to decide some starting point and then add up the vertices relative to that vertex. So in this algorithm, the minimal spanning tree, expand outward in connected links from some vertex. One edge and one vertex are added at each stage. The edge added is one of the least weight that connects the vertices already in T with those not in T, and the vertex is the end point of this edge that is not already in T. So what is this algorithm? This is explained here in this slide. Basically the input is any graph G which is connected and has n vertices where n is positive integer, the same input as in Kruskal's algorithm. Algorithm body, basically this algorithm builds a subgraph T of G by starting with any vertex V of G and attaching edges with their endpoints. one by one to an as yet unconnected vertex of G, each time choosing an edge of least weight that is adjacent to a vertex of T. So first step is basically in this algorithm is pick a vertex V of G and let T be the graph with one vertex V and no edges. But that is, we remove all the edges from that graph. We just mark the vertices as we have done in the Kruskal's algorithm, and we select one vertex where we have to start this Prim's algorithm. The next step is let V be the set of all vertices of G except V. From I1 to n-1, find an edge E of G such that E connects T to one of the vertices in V. 2 is E has the least weight of all edges containing T to a vertex in V. Let W be the endpoint of V, endpoint of E, that is in E. The 3b is add E and W to the edge and vertex sets of T and delete W from V. Next I. Output is the minimal spanning tree. So let's discuss this algorithm with the help of the same graph which we have discussed for the Kruskal's algorithm. In this graph we have to find again the minimum spanning tree with using Prim's algorithm. And in this algorithm, you either in the example or in the question the starting point is given, or you can select the starting point yourself if the starting point is not given. The starting point is given here, Minneapolis. So we have to start finding the minimum spanning tree with this city, Minneapolis. Here we have the starting point. Again we draw all the vertices here, or you can say the starting vertex only, and then we see all the edges which are connected to this point and who has minimum weight. So there are two edges which are connected to this vertex, and one has weight 355, the other has 695. So we pick up this edge and we connect this vertex to this vertex having 355 edge. Now we see both the vertices. For example, here this is basically at iteration 0 is the starting point. The first iteration is we connect Minneapolis with Chicago, which has weight 355. Now we see both these vertices, and we see that whether there is an edge who has minimum weight. With this vertex we have only one edge which has 695 weight, and with this vertex we have this one, we have this one, and this one. Now which one has minimum weight? 74 is the minimum weight, so therefore we connect this 74 with the vertex here. And we have to care about here that we don't get any circuit in connecting these vertices using Prim's algorithm. Now we have three vertices. Now we see all these three vertices, and we see the weights of all these edges connected to these three vertices. We have 695, we have 262, we have 348, we have 269. So all these edges are connected to these three vertices, and minimum weight among all these vertices edges is basically 262. So we connect 262 with the St. Louis, this city which has 262 weight. Now we see all these vertices and the edges connected to these vertices, and we find the minimum weight. So this one is connected to this one, which has 242, it has 262, 269, 348 and 695. So minimum weight among all these edges is 242. So we connect St. Louis with the Louis wheel. So 242, we connect this. Still we don't have any circuit with this in this connection. Now we see all these vertices and the edges associated to these vertices, and we'll find the edge with minimum weight. We have 151, 83, 306, because with this we have connected this one, this one, this one, and with this we have connected this one, this one, this one, and this has already been selected. This is already selected also. We have this one, this one, this one, this one, this one, this one. So the minimum weight among all these edges is 83. So we connect this Lewis wheel with now we see all these vertices and edges which are connected to these vertices, and we try to find the minimum weight. So this is basically, you can say, 151. So we connect this with Nashville because the weight is 151. Here we have 83, and we connect it with Detroit, which has weight 230. So with the help of Prim's algorithm, this is how we can obtain the minimum spanning tree. The result is basically here. First we add 355, then we add the edge which has weight 74, then 262, then 242, then 83, then 151 and 230. So the solution is basically with the Prim's algorithm is this one, and this is basically the minimum spanning tree, which is same as obtained in Kruskal's algorithm, which has the same weight. So this is how we can find the minimum spanning tree by using these two algorithms. Now let's consider another example in which we have to find the minimum spanning tree. Find all minimum spanning tree for the following graph using Kruskal's algorithm and Prim's algorithm, starting at vertex A. Indicate the order in which edges are added to form each tree. This is another example, just a different example, how to apply these algorithms in finding the minimal spanning trees. So when Kruskal algorithm is applied, edges are added in one of the following two orders, because in this graph you can see that we have edges having same weights, so there are multiple possibilities of adding edges. So the starting point is A, therefore not for Kruskal's algorithm, a starting point A is given for the Prim's algorithm starting at vertex A. So for Kruskal algorithm we shall find an edge which has minimum weight, which is this one, so we add DF, and then minimum is 2, so we add AC, and then minimum is 3, we add either this or this, so we can add AB or BC. Here we have two possibilities, the rest is same. So if we add AB, then we'll add this one, and then further we have 4, so we added CD, and then we have 5, so we added DE. So this is, we obtain the minimum spanning tree. And the other possibility, you can see that we can add either this one or this one, then this will change the minimum spanning tree. This is how we can apply the Kruskal's algorithm. Now and we obtain this graph by using Kruskal's algorithm. This is basically the minimum spanning tree, or if we remove this one, we shall obtain. Now by using Prim's algorithm, the starting point is A, therefore we add this one because it has less weight than AB, which is 3. So we add AC, and then what is the minimum weight of both these 3, so we can add either this one or this one. So we add AB here, and in the second option we add BC. The rest is same. Now we see all these three vertices and the edges connecting these edges and having less weight is basically CD, which is 4 CD, because this is 6 and 4 is less than 6. And then we have 1 is the less weight, and then we have 5 because 6 is greater than 5. Therefore we obtain this spanning tree with the help of Prim's algorithm. You can see here that this spanning tree is different from this one. So if we add up, we select this one, this will be, both spanning trees will be same and both have same number of edges. So this is how we can find the paths and with the help of minimum spanning trees. So for trees it's enough. We have discussed all the necessary and important topics in trees. For today it's enough, and let's sum up what we have discussed today. Today we have discussed rooted trees, binary trees, and then spanning trees and shortest paths, minimal spanning trees, and we have discussed Kruskal's algorithm, Prim's algorithm, and how to find minimum spanning trees. So today our discrete mathematics course has been finished, and we have discussed and mainly these topics. The syllabus which we have covered in this course is basically, we have started with logic, predicate logic, and logic of quantified statements. We have discussed all these topics, and we have discussed some applications of logics in digital circuit designs. We have we have discussed parallel adder, what is parallel adder, and how to add the binary numbers with the help of circuits, and which are how to add binary numbers with the help of circuits. And we have also discussed some basic circuits of digital logic design, and then we have discussed elementary number theories, and then how to prove a given statement. And in this we have discussed different types of methods of proofs. We have discussed also the set theory, the basic properties of sets, and then we have discussed in this course the relations, equivalence relations, and how they help us in computer science. We have also discussed sequences and summations, and another method of proof which is very famous which is basically the mathematical inductions. We have also discussed counting, what are permutations, combinations, and how to calculate, how to simplify such type of mathematics in this course. We have discussed also the functions. Function is basically a special type of relation which satisfy certain properties. And at the end we have discussed graphs and how graphs help us in computer science. And further at the end we have discussed trees, how they help us in finding shortest paths in real life problems, such like just like as we have discussed one example of expanding their service. An airline want to expand their service. So I hope you understand not all but maximum of these topics and maximum of things which we have discussed in this course. And good luck for the exams and assignments, and for the final exam of this course. Prepare well and try to get maximum grade in this course, because it's in my opinion it's an interesting course. You will enjoy doing the exercises of this course. For exercises related to each topic, logic, elementary number theory, relations, etc., I have told you in the first lecture the reference books, which are basically discrete mathematics and its applications with combinatorics and graph theory. It's you can take its either 5th, 6th or 7th edition. It's written by Kenneth H. Rosen. The second option for the exercises or related to the topics which we have covered in this course is basically discrete mathematics with applications. You can take its 2nd edition or 3rd edition, which is written by Susanna S. Epp, or you can take discrete mathematics for computer scientists 2nd, 3rd edition, which is written by John Truss. I have consulted a maximum of these 2 books in preparing these slides and delivering these lectures. Maximum, basically this book of Susanna, I have prepared maximum of the slides at the end, after the, you can say, 16th or 17th lecture. I have consulted the book of Susanna, but in the early lectures, 1st to 5 or 6 lectures, I have consulted maximum of the book of Kenneth H. Rosen. So you can discuss, you can find exercises in these books and just practice maximum of the exercises to master this course. So good luck for this course and good luck for the future. Allah Hafiz.